and we go on to Adam Jermyn's talk. Would you please share your slides and we see if everything works correctly?
Yeah, so hopefully this works.
Yes.
Okay, great. So it's been really fun seeing all of the science that people have been doing. I thought I'd talk about a project that started at the Exostars program with Jamie Tyrer and Jim Fuller, where the goal was really to see if we could use some tidal theory and observations of eclipsing binaries to place constraints on differential rotation. So just as a quick overview of what we're thinking about in terms of tides when there's no differential rotation, you have two stars. They have their own angular velocities, which may be different from one another, and may be different from the orbital angular velocity as well. And the gravity of each star raises a bulge on the other, and because there are internal hydrodynamic processes, this bulge generally lags relative to the line of sight between the two stars. And so, because the bulge ends up lagging and misaligned, there's a torque, and that torque generally acts to synchronize the stars to the orbit, at least in the circular case where there's no eccentricity. So that's sort of the picture when everything is a solid body rotator. But we know from heliososmology that at least one star is very, very definitely not a solid body rotator, right? So the sun has something like a 50% shear between the pole and the equator, and maybe 15% across the convection zone in the radial direction. And so if we're thinking about, say, like Kepler eclipsing binaries, where many of them are solar type, maybe we should really be thinking about them as differentially rotating. And so the question that we really started with is does the differential rotation survive the tidal torque, right? Do you maintain differential rotation in the face of tides? And if you do, then what exactly do we mean when we say that the star synchronizes, right? It can't just be the whole star is now rotating at the orbital rate. It has to be something more subtle than that. So on that first question, thinking about the sun, we have a transport process. There are some transport processes that we think are active in the convection zone that actively pump angular momentum, and this pumping is what maintains the differential rotation. So if you think there's a characteristic timescale for some transport process, and that's what generates the differential rotation, then I think the answer to the first question is just set by basically how that timescale compares to the tidal synchronization time, right? So if that timescale is very long relative to synchronization, then the tides act quickly, much faster than whatever the star is doing can react, and so the tides control the shear. On the other hand, if the transport process is really fast, the timescale is short, then whatever intrinsic shear the star wants to have is what it's going to have, and the tides are a perturbation on top of that. And so this really depends on what's happening inside the star to transport the angular momentum. And to first approximation, you can sort of separate that part into radiative zones and convection zones. And while there's been a lot of work in recent years, including by many of the people here, on what transports angular momentum in radiative zones, I don't think I can at least make a strong statement about a timescale separation in those. But for convection zones, I think there's a very strong statement, which is that the angular momentum pumping time is something like the convective turnover time, and that's just because you're physically exchanging fluid elements. And that time scale is a month in the sun, something like that, versus the 100 million years that it might take to synchronize your binary. And so there we have a very clear separation of timescales, and it's quite clear, I think, that the differential rotation should survive. So if we take that view, then we have to answer what synchronization actually means. So here I'm showing just sort of a toy model, a rotation profile with some function of radius in the star, The little points correspond to the picture below. And in this, what I want to do with this toy model is try to build some intuition for what synchronization could mean. So in this case, the orbit, as I've drawn it, the orbit is much faster than the rotation of any part of the star. And so we predict that what happens is the star spins up. That every part of the star is receiving a torque in the same direction, and that it's all spinning up. And so there's a net injection of angular momentum into the star. And we can look at the opposite limit, right, of a very slow orbit with a very rapid star. Here, everywhere in the star is going faster than the orbit. And so we think that then everything ought to be spinning down. And so there's a net extraction of angular momentum. And so because the total change of angular momentum changes sign between these two scenarios, there has to be something in between where there's no net change in angular momentum for the star. And so this is sort of what we think synchronization looks like for these stars, namely that some parts of the star are spinning faster than the orbit, and those are going to be spun down by the tidal torque. And some parts are spinning slower, and those will be spun up. But then because you have an active angular momentum transport process happening in the star, angular momentum gets taken away from the places where it's spinning up and placed in the places where it's spinning down. So you build a conveyor belt that allows you to have both the net torque be zero and have the angular velocity be in steady state. So this is the definition we'd like to suggest for synchronization in these cases. And importantly, this means that the surface period of a synchronized star may not equal the orbital period, even if the orbit is circular. So that's sort of the prediction we want to use to then measure differential rotation. We want to turn it around and make a measurement. So to do that, we use this catalog of eclipsing binaries with measured rotation periods from Lurie in 2017. And our hope was that by looking at the shorter period ones, the ones where we're pretty confident, out at 0 to 10 days or something, that they are actually synchronized, that we'd be able to then use differences between the orbital period and the rotation period to get a measurement of differential rotation. So we set this up as an inference problem, and to do that we had to assume a toy model of what the rotation profile of the star looks like. So the profile is a power law and radius with that power law exponent as a free parameter. And it's just a low order spherical harmonic in the latitudinal direction. And so we figured we can calculate things with this toy model. That was the first advantage. And the second is it does a pretty good job of fitting the sun. So in the sun, beta is something like 0.15, and delta log omega is like 0.3, 0.4. So then we did, you can then integrate over the volume of the star and set the torque equal to 0, assuming this profile. And that gives you a prediction, setting that to 0 gives you a prediction of the ratio of the orbital period to the surface period. So some of this we get out analytically, that's the latitudinal part, but the radial part depends on the stellar structure. And this is for two reasons. One is that the tidal torque depends on the density in part, right? The specific torque doesn't, but the actual net torque you accumulate does. And the other is that the dissipation, we think, depends on the convection speed. So for each star in the sample, we had to have a MESA model to compare against. So what we did was we used the Kepler reported temperatures, that we assumed that all of the objects were on the main sequence, and we picked the mass to match the temperature. So it's a very crude thing, but it gives us enough to calculate this thing we're calling K-star. And with that, we then went and fit different sort of windows in period space. So in this case, we started by fitting the 0 to 2 day period window on the theory that those very short objects are the ones most likely to actually be synchronized. I should note the vertical scale here is really small. There's actually very little deviation at these very short periods. It's maybe 2%. Now, this is much slower than what you saw a few slides ago, and that's because, A, we filtered for just circular orbits, and that removes a lot of the scatter. Then we removed any known pulsators, known triple systems, and the prevalence of those led us to then build a very simple outlier model. And so I've also not shown the outliers here. But the fact that the scale bar is so small, it's 2% variation, automatically tells you that these stars can't have as much differential rotation as the sun. Right? The sun which would be many pages off of this chart. So that's sort of the first hint that maybe there's something that we've got something interesting. So we did a sort of a fit to this population, assuming that the radial shear parameter is constant across all of the objects, and letting the latitudinal shear vary a little bit with orbital period. So the parameter lambda ends up being our proxy for the latitudinal component. And what we find is beta is very nearly zero. There's almost no radial shear in these stars. And maybe there's latitudinal shear, but everything we see is consistent with zero. And this is a very different story from the sun. If you put a sequence of objects, all of which look like the sun, and do the same analysis, you should find something very different. So we then repeated that for different period windows. So 0 to 2, 2 to 6, 6 to 10, 10 to 50. Maybe you don't believe 10 to 50 is synchronized. I probably don't. And we keep finding, we can place constraints, and as we go out to longer periods, the constraints we can place get weaker. But we never actually managed to get a non-zero measurement. Even so, I think the constraints themselves are actually interesting. And to show that, I want to compare this with a little theory. So here I'm showing on the vertical the radial shear. Horizontal is the inverse Rossby number. So rapid rotators are on the right, slow ones are on the left. The solid blue line is a prediction that I made in this recent paper. And I've overplotted a few measured objects like the sun and Jupiter and so on. And so we can add these new constraints to this plot. And you can argue over exactly what the correct way to do the Rossby number conversion is, but doing something that I think is reasonable, we get these points. So these are upper bounds because we get constraints, not actual measurements. But it's at least encouraging to see that they don't rule out the theory just yet. But also that the strongest of these are very definitely below the sun. So we're definitely placing a bound that says these objects, even though they're solar mass, they're like one solar mass, they're not like the sun. So I'll leave it there and just mention, so this project started, I think Jim got us started thinking about this question over coffee at KITP in the afternoon, and then we sort of spent the rest of the afternoon working on the board by the coffee. And if you look at the paper, a few of the numbers are different, but a lot of the equations in the paper end up being pretty similar to what's on the board. So thanks.
Thank you, Adam. Great. So do people have one or two questions they would like to ask right now? You can either raise your hand in Zoom, or you can type something into the chat window. So let's see. So I have a quick clarification question, Adam. In that final plot you showed just before this one, exactly that one. So for Jupiter, the red line is also all upper bounds, right? But for the orange line so are these all upper bounds except for the blue data point, or is the orange and the green things that have been detected somehow?
The orange and the green, I believe, are actual detections. So the orange is calculated from just the solar rotation profile, and the green and the red both come from Juno measurements, but they get a measurement at low depth, and then they get an upper bound at high depth.
I see. So. Okay, great. Thank you. Yeah. So if you have other questions regarding to this, please type them into the chat window so that we keep them for later.